big structure.
The San Andreas Fault is one of the best-known geological features on Earth. Some of it is easy to see, but parts of it are kind of hard to find unless you know what you're looking for.
Because these sag ponds...
And if you live in Southern California, some say it's just a matter of time before it will find you.
Right. The fault's just running right through town.
Funding for The Desert Speaks was provided by Desert Program Partners, representing concerned viewers making a financial commitment to the education about and preservation of deserts, and by the Stonewall Foundation.
The southern end of the San Andreas Fault lies in southeastern California. The fault extends nearly 800 miles to the northwest. Along it, human beings have experienced enormous disasters throughout its history and will experience even greater catastrophes in the future, perhaps the near future. But in various places along the way, there are gardens of Eden for geologists. That part of Southern California lies in the driest desert in the United States. It's a geologist's paradise because the hyper-arid climate leaves geological evidence exposed to the naked eye. The surface gives us clues about the real action that is happening miles below the surface. It's here where the tectonic plates, continental-sized sections of Earth's crust that float on the Earth's mantle, are engaged in a brutal struggle. Geologist Susan Beck is an interpreter of that struggle that, by the way, is the source of earthquakes.
There's three types of plate boundaries. The first type is a subduction zone where the plates are moving together and one is diving down underneath the other one. Those are places where you generate big earthquakes where the plates get stuck together, and you also generate big volcanoes, some of the biggest in the world.
An example of this is the 5,000-mile-long steep mountain range known as the Andes, a region of nearly constant earthquakes and exploding volcanoes.
A second type of plate boundary is where the plates want to move away from each other. Material comes up and you're forming new material at the surface of the Earth. A great example of that is the Sea of Cortez and the southern part of the Salton Trough. A third type of plate boundary is called a transform plate boundary, where material slides past each other and still gets stuck and generates big earthquakes. And a great example of that is the San Andreas Fault.
It started 4.5 billion years ago with the formation of the Earth, and it's
Field geologist Bob Powell has spent the last 30 years clambering over, photographing, and digging into the land along the fault, what's known as the fault zone.
The San Andreas Fault is named after San Andreas Reservoir, a lake in the south of San Francisco. And the reason it's named San Andreas Fault is because the 1906 earthquake happened on that segment of fault. Humans live years, they live decades. A few of the fortunate ones live a century or a little more. But all of that is a very small amount of time in geologic time. So as we think about the evolution of the San Andreas Fault, it all starts when the Pacific plate and the North American plate came into contact. That happened about 30 million years ago. 30 million years is an inconceivable time for human beings.
The San Andreas Fault is increasing length, and the Pacific side is moving north relative to the North American side of the plate boundary.
Our trip along the San Andreas Fault begins where there is constant evidence of the ongoing underground battle. Several decades ago, some people realized that at the southern end of the Salton Sea in Southern California, there was a lot of heat energy coming out of the ground, mud pots, even small fumes of steam. They did a little drilling and found that the farther down they went, the hotter it got. And finally, they found if they went down a mile or so, the temperatures were over 600 degrees. What a great idea to pump water down and let the earth do the heating rather than using fuel. And now there are 10 power plants around the Salton Sea. Here, that deep battle is tearing the earth apart, causing a cosmic indigestion and an unending belching of gases to the surface from far below.
As you watch the material come up, you can see that there are two modes. One is a kind of splattering that just throws out great blobs. Another one oozes out as a liquid and moves down the slope, and it even has kind of mud flow and glacier type forms. I think that fluids are actually being driven from very deep, maybe even that 3 to 5 miles we're talking about. The Salton Sea has now been evaporated away and has retreated from this area, but the muds remain, and that we are also over an area that is a spreading axis wannabe. It's pulling apart down there, and then the thermal energy is coming up, outgassing is going on, and the system is working its way through those muds and mobilizing them to form these volcanoes.
We know there's a lot of sulfur, we can smell that. We know there's a lot of carbon dioxide coming out. Those are typical gases, again, in volcanic centers that you often see. And it's pressurized at depth, and so it's trying to find ways to escape, and this happens to have fractures that it can come up along.
The mud pots are no more than a couple of acres in distribution here. They're called mud pots, perhaps because of the variety of sounds. There are blubs, and there are gurgles, and there are hisses, but there are also schlibs, glebbles, schlarps, and ultimately glimps.
Now we come to the volcano itself, and you can see the mud is just a little bit more viscous. It wants to hold together more, and it explodes out of there. Whereas over here, the mud is a little bit more willing to flow, and it oozes out and flows down and forms these complex curving bumps as it moves
This thing
along.
fights back.
Yeah.
So do you think Pele, the Hawaiian goddess of volcano, was involved in this?
I don't know, maybe a distant cousin.
The Salton Sea region, with its mud pots and geothermal plants, is like a huge watering trough set on quicksand. It is gradually sinking. I guess we can descend to the bottom of the world.
We're about 230 feet below sea level at this locality, and the Salton Sea out here is got about 50 feet of water in it. It's pretty shallow, and it's right in a basin that's pulling apart, and the bottom is sort of dropping out.
How fast?
Well, it's dropping down about 1 or 2 inches a year, actually.
So it could be within a couple thousand years, this will be the lowest place in the Americas.
Yeah, I think that's a pretty safe thing to say, that this will catch up and surpass Death Valley.
The Salton Sea is not connected to the Gulf of California because of the Colorado River. The Colorado River is dumping sediment into the trough. As the trough and the Gulf opened, starting about 5 million years ago, that gave a place for the Colorado River to dump into. The Salton Trough is continuing to drop, and every once in a while the Colorado River will flow towards the trough off of its delta. Think of a river coming down. Sometimes it goes this way, sometimes it goes that way. When it comes into the trough, it fills the Salton Sea. When it does that for long enough, the water that's in the trough here gradually evaporates, creates a salty lake, eventually dries up, creates what we call a playa, and then the cycle repeats itself. And that's happened over the last 50,000 years several times.
Near the northern end of the Salton Sea, we get a first-hand glimpse of the power of a moving fault to deform ordinary, everyday rock. Force it up, flip it over, tear it apart, flop it on its side, even to bend it. On each side of the fault, its movement produces enormous cracks that connect to the main fault as side faults, like slowly pulling apart a piece of birthday cake. It doesn't tear neatly.
When you come to a place like Painted Canyon, it gives you the opportunity to see extraordinary deformation, and it turns out that that is within a greater San Andreas Fault zone than just the simple strand that we follow now and again. And what we're seeing in this canyon is the effect of that kind of step in a fault system that leads to this contraction. And the powers that do this, the same driving mechanism that allows you to move the San Andreas Fault and has the ability to lift up these hills and fold the rocks that make them up and break them around those folds and still keep moving the countryside along the plate margin. But the effect is so powerful that it's causing faults that extend 70 kilometers that way. There are faults 50 kilometers that way that are taking up a significant portion of the plate margin boundary. This is active geology. We see them as static, but this stuff is going up, moving along. Pieces over here are sliding past one another, all to accommodate this plate margin.
When I look around in this canyon, I see colors, I see shiny rocks, rocks made out of sand, gravel, all in a jumble. How does the San Andreas Fault do that?
Imagine trying to bend a piece of glass. That glass just doesn't want to bend,
So it breaks.
So it breaks and it shatters. And now you get a little bit of bending on these rocks that we're looking at that are colorful, but pretty much they're, as you've tried to do that, they're broken and shattered to accommodate that attempt.
And they wind up
them.
then at all crazy angles.
And all crazy angles. You have to think in really 4 dimensions, the 3 spatial dimensions and time. I'm a geologist because I absolutely love the challenge of trying to figure out that kind of history. Once a geologist, always a geologist. You live and breathe geologist. You go on vacation and you're looking at the geology and explaining it to your daughters. And they're groaning and moaning, but they're loving it. You know, wherever you are, there's the landscape, and the landscape has a geologic story.
The San Andreas Fault is not perfectly straight. As you come through Southern California, there's a big bend in the fault that we call the Big Bend. And it's very important because as the fault goes through that bend, it causes a lot of compression across it, and those forces, it splays the fault, breaks up the ground into many different fault splays. The mountains are going up, but what they actually do is they go up a few feet every time there's a big earthquake. And so by repeating that process over thousands and millions of years with thousands of earthquakes, they incrementally go up.
You can't have mountain building without valley building. As we move northwest into the bend, the valley gets narrow and becomes pinched between 2 ranges, creating an uphill funnel. That constriction into a pass provides humans the opportunity to harness another form of energy related to the San Andreas Fault. The existence of the world's largest wind-generating system here near San Gorgonio Pass in Southern California is due largely to the effects of the San Andreas Fault. Here to the west, the fault runs into obstruction and bends, forcing a constriction in the valley and a pass. The air around the Salton Sea, also created by the San Andreas Fault, is heated. It's a very hot area, and as that hot air rises, it creates convections, which move westward into San Gorgonio Pass, where it is funneled. And hence we often get huge winds here, the ideal place to create a wind-generating system. Thank you, San Andreas Fault. The winds that are caused by the effects of the San Andreas Fault can do strange things, even to rocks. This rock is an example of a ventifact. That's a geological term for a rock that has actually been sculpted by blowing sand. The wind prevails here from the west. The grains of sand blowing over this rock have smoothed it out, have actually sculpted nice little crevices in here, and have smoothed the entire rock very much as though a glacier had flowed over it. It's an example found not in many places, but a hard rock like this has no defenses in the long run against the wind and the sand.
Desert Hot Springs, California is a town that's really built right on the San Andreas Fault, and it started that way because there were a lot of hot springs there along the fault, so it was a great place to settle and build resorts. The population has grown tremendously, and it's still sitting right on the San Andreas Fault zone. We know that this segment of the San Andreas last ruptured in a major earthquake in 1680. And it's been 300 years. You can sort of imagine that eventually that lock segment of the fault is going to slip. And that's a lot of people sitting right on top of the San Andreas Fault zone.
What Susan and Bob have shown me along the fault have convinced me that we can't get the big perspective from the ground alone.
You can really see how Desert Hot Springs is right up against the mountain front and right along the fault. And the water comes up along the fault because you get different rock types that help hold the water in along the fault. That's where the springs are. You also get a lot of water coming out of the mountain ranges. And those mountain ranges are due to the fault system as well.
Obviously, the urban center is built where the water is easiest to get.
That's right.
And you can almost see down there that these cities follow the fault.
That's right, but of course that's why they built there in the early days. It was, that's where the water was in the springs, and if you come out to this desert, well, you're not going to live anywhere that there's not water. The trace of the fault is just coming right along the base of these hills.
So it actually, you can see the place where the fault lies.
One side is up where they've been crinkled, and this side is pretty flat. So right at that change in topography is where the fault comes through. You just follow the water. But right there, that clump of vegetation is the fault coming through. So here we are, just headed right down the fault. Just dropping off. I'm just amazed at how you can see the fault by the vegetation along here. There's groundwater everywhere, and faults, when they break up and fracture the rock, it makes little spaces for the water to come up along
it'll be
there.
solid rock otherwise.
Yeah,
they break it up and the water can come
That's
up.
right. When those plates move, it's just grinding up rock down there. You can imagine how it must be grinding it up into small pieces, and that allows space for the water to come up. You see that red clayish looking material right along the fault, just squeezed up.
Like toothpaste squeezed out of a tube.
Yeah.
That red stuff is pushed up there.
Look at the palm trees. These palm trees wouldn't be here if it weren't for the fault.
How did you decide to become a seismologist?
Well, I grew up in Colorado and Wyoming, hiking and camping in the Rocky Mountains. And I always was fascinated by the mountains and the rocks and how they all formed. And then I realized if you want to study that, you study geology. And so that's what I did. And got fascinated with how mountains formed and realized a lot of what happens with forming mountains are due to earthquakes. And earthquakes are something that's really happening now and impact society in a way that really fascinated me. So that was it. I've never looked back.
And this is sort of earthquake heaven, if there can be such a place.
Yeah, California is really earthquake heaven. In fact, the whole western U.S. is just a fascinating place with earthquakes.
It's hard to imagine the damage it can do, though. It's not just the destruction of houses and buildings falling over and toppling and roofs caving in. Gas mains are broken. You get fires.
There's a lot of damage to the infrastructure, and a lot of the infrastructure is almost harder to rebuild than a house. But you know, there's a lot of things people can do to get prepared for an earthquake. You can first of all look around your house and know where to turn off the gas lines and the water lines in case of an earthquake. But what you really want to do is think about how to keep your family safe in the case of emergency.
Between Palm Springs and Los Angeles, the fault splits the very mountains it has created. Now we have to look for signs of the fault in a forested landscape. It takes a trained eye to see the same titanic struggle that was so obvious below. This is one of these gorgeous messes. What's going on here?
We are right now at the edge of the San Andreas Fault zone, which is here 200 or 300 feet thick, and we're at the edge of it up against granitic rocks of the Mojave Desert. What we're looking at here is the San Andreas Fault zone exposed at depth, but it's been lifted up here so that you can see it, and the rock has just been beat up. It's been ground down, it's been pulverized, it's been really hurt
This
as
is
the
the
fault
edge.
has moved. This is the edge of it.
This shows the power of the movement of the plates to take big rock and reduce it to nothing, but leave other larger pieces inside.
And it's going to get ground down even further as we move deeper into the fault zone.
It seems a little incongruous to be a mile away from the gouge zone and then find a pond full of cattails up here high in the mountains.
Well, this is a pretty impressive place. We're along the San Andreas Fault, but it makes a little step over and creates a little basin that fills with water. It not only fills with water, though, it fills with peat and organic material, and that's really important for dating earthquakes. Look at this mucky stuff. So when this gets caught in the fault during an earthquake, you can take this material and date it with carbon-14 dating.
So there will be layers of peat in the historic record, and you can date them, and you know when those happened that there was an earthquake.
That's
at that
right,
time.
and when you see it caught in the offset of the layers, you can date it.
What keeps the water from running out? If you've got the plates moving back and forth here, why doesn't it just drop way down deep into the earth?
Well, there's probably a clay layer that helps keep the water in. This is also another important place because this is a segment of the San Andreas that ruptured in 1857. A pretty famous earthquake if you're an earthquake seismologist.
How big was it?
Was a magnitude 7.9, and it ruptured 250 kilometers of the plate boundary, including this region right where we're standing. It took about 3 minutes to rupture that 250 kilometers or so. That rupture would have been propagating along about 2 or 3 kilometers a second. So you can see the evidence of the earthquake, and then you can use this to get the timing of the earthquake. And here we've got a record back about 6,000 years and about 30 different events that have happened. And that gives you an average recurrence interval rate of about 150 years. And let me remind you, the last big earthquake was 1857.
Let's see,
So
that's
you
about
do the
100.
math.
Are you concerned that if the word gets out that this is so good for earthquake seismology, they may overcrowd the place?
Earthquakes, like music, can be amplified. The shock may be greater at a distance than at the precise site of the quake. No place on Earth has received as much geological attention as the San Andreas Fault. As a result of this, we have complex and precise maps. By overlaying dozens of maps in millions of bits of data, scientists can demonstrate the ominous future the earthquake zone faces.
Well, this is a map that shows the amplification due to site effects. In other words, what you're sitting on, how much that will amplify seismic waves. Here's I-10 coming across. Here's the San Andreas. And look at these colors. There's blue and red and yellow. And this color code is simply the amount of amplification relative to some shaking, where yellow is the most intense amplification, red is sort of intermediate, and blue is the least amount.
So you get a little shake and it gets bigger and bigger and bigger and bigger.
Yeah.
Whereas you may just get an initial shake, jolt, and stop here then.
Yeah, the seismic waves get into those basins and sort of rattle around.
So here's the Los Angeles area down in here then.
Yeah, this would be Los Angeles in this region, and this is the trace of the fault.
Then Long
out
Beach
here.
is down in
Yeah.
here somewhere. So the most densely populated
Populated
part of the
regions.
basin is where you're going to get the highest amplitude. Not a pleasant prospect.
The southern San Andreas Fault has two segments that we know have had large magnitude earthquakes, and I mean by that magnitude 7.8 or 7.9. But those earthquakes tell us that the San Andreas in this region is capable of big earthquakes. And so we have to think in terms of what if those earthquakes repeat again, which they certainly will.
There's a cliche among geologists about the San Andreas Fault that it's not a question of if a major earthquake will occur, but when. Geologists are understandably reluctant to predict precisely when it will occur. But given those uncertainties, a prudent policy would be for geologists to continue their research and the best possible information made available to the public so that when the big one happens, which it must, the damages will be minimized.
Many sorts of vines are native to the Americas, but the domestic grapevine is not among them. Somehow, though, these hardy plants are doing very well in the arid climates of central Chile. Vines dominate the landscape, and wine production dominates the local economy. There, wine is more than just a beverage. It's a way of life and part of family values, just as it has been for generations of Chileans.
It does help to be able to see it from above, and you can see pretty graphically how the forces have resulted. If you're on the ground, you have to do a lot more figuring out than you do if you're looking at it from above. You say, holy cow, what an unbelievable force.
And you realize it's not just this little bit right here, but there's a whole mountain range of crushed and tortured rock.
Funding for The Desert Speaks was provided by Desert Program Partners, representing concerned viewers making a financial commitment to the education about and preservation of deserts, and by the Stonewall Foundation,